and welcome again. Let's talk today about solving systems of linear equations by graphing. So get yourself some graph paper and a pencil and a straight edge. I've got mine. And we're going to be doing some thinking. So thinking and writing must always go together. So get your materials together. Let me share with you my desktop. So you should be seeing my document camera today. So what we're going to do, we've got a graph y is equal to negative x plus 4 on the Cartesian grid below. Remember that we're going to graph it using slope-intercept, so y is equal to mx plus b. I'm going to graph the y-intercept, which is positive 4, so I'm going to go up 1, 2, 3, 4, graph that point right there. And then my slope is going to be negative 1, so that means down 1, right 1. So I'm going to go down 1, right 1 a couple times. And I'm now going to get the line that looks like this. Let's see if I can draw this in an awkward physical position because of the camera, but we'll see if we can do it. I think that's it. Good. So now the questions here is 1, 4 on the graph of the equation. Well, let's see, go to the right one, go up 1, 2, 3, 4. That's that point right there. My initial answer is no, but it says show analytical justification. What does that mean? Analytical justification is algebra. So what does algebra have to do with this? Well, remember that the graph of an equation is the collection of all the solution points. So if it's a point that's on the graph, it will solve the equation. Remember, this is an x value and a y value. So that means if it's not on the graph, it shouldn't solve the equation. So let's check it. I'm going to take this x and this y value and plug it into the equation there and see what I get. So the equation is y is equal to negative x plus 4. I'm going to plug in my y value of 4. Is 4 equal to, I don't know, I'm asking. So I put a little question mark over the top. Is y equal to negative of the x value, which is 1 plus 4? That's going to be negative 1 plus 4. Is 4 equal to 3? No, that's a false statement. So there we go. I've just shown you analytic evidence as to why it's not on the graph. Let's try B. Is 3, 1 on the graph of the equation? Well, let's check here. Go to the right 3, 1, 2, 3, and then up 1. It looks like it is. But if it is, it must actually solve the equation. So let's try it. Y is equal to negative x plus 4. I'm going to plug in my y value of 1. Is 1, I don't know, I'm asking. Is 1 equal to negative of the x, which is 3, plus 4? This is going to be negative 3 plus 4. That's true. So the answer, yes. Okay. Both graphically and analytically. Now the last one, is 6, 3 on the graph of the equation? Well, all right, so 1, 2, 3, 4, 5, 6, and then up 1, 2, 3. Oh no, that's way off. Let's see. Y is equal to negative x plus 4, so the y value is 3. Is it equal to, I'm asking, negative of 6 plus 4? Is 3 equal to negative 2? No, way off. There we go. Nice, huh? Okay, good. So now what about this one, activity number 2? Graph that on the Cartesian grid below and do the same thing. Well, all right, so I'm going to plot the y-intercept here of negative 1. So I'm going to go down 1. That's that location there. And then my slope is 2/3, which means I'm going to go up 2 and then right 3. So up 2 and then right 1, 2, 3. There's a point. And do it again. Up 2 and then right 1, 2, 3. There's a point. Okay, now get out my straight edge. And let's see if I can graph that neatly. I need to be very, very precise on these graphs. You should too. You'll find out why in a momento. There we go. Okay, is 1, 4 on the graph of the equation? Wait a minute. Isn't it the same question I asked right up here? Yes, it is. This is 1, 4, 3, 1, and then 6, 3. Same things here. 1, 4, 3, 1, and 6, 3. Okay, let's run it again. Is 1, 4 on the graph? So let's go over to 1, go up 1, 2, 3, 4. No way, man. That's way off. No. Show analytically. Okay, so what was it? It was y is equal to 2/3 the x minus 1. So to give myself some room, I'll go to the right here. So is the y value, which is 4, equal to, I'm asking, 2/3 times the x value, which is 1, minus 1. Is 4 equal to 2/3 minus 1? Isn't that like a negative 1/3? No, that's a false statement. Okay, there we go. It's not on the graph. How about 3/1? Is that on the graph? Well, 1, 2, 3, up 1. Well, look, there it was. Wait a second, was 3/1 on the graph of the other one? Check. But anyway, so y is equal to 2/3 x minus 1. Plug in the values. The y value of 3, no, the y value is 1. Is 1 equal to 2/3 times 3 minus 1? Is 1 equal to 2/3 times 3? The 3's cancel and I get 2 minus 1. I get 2 minus 1, that's 1. Oh, that's a true statement. So yes, it is. It was also on the other one earlier. Imagine that. All right, so C is 6/3 on the graph of the equation. I'm betting no, because like this one wasn't on it, and like this one wasn't, but this one was, and the third one wasn't. So if I were to say, I'd say like, you know, we're going to do the same thing here. So let's check it. So 6/3 to the right, 1, 2, 3, 4, 5, 6, up, 1, 2, 3. Oh snap! That point is on the graph of this one. Well, okay, it's a separate equation, right? So yes. Let's try it. Y is equal to 2/3 x minus 1, and then we put in the y value. 3 equal to, is it? 2/3 times the x, which is 6 minus 1. Is 3 equal to? 2/3 times 6. This 3 cancels completely and leaves me a 2 here. So 2 times a 2, which is there, which is 4. 2 times 2 is 4 minus 1. Is 3 equal to 4 minus 1? Happy, happy, joy, joy. Yeah. Nice, okay. So remember that the solution points lie on the graph. The graph of an equation is the collection of all of the solution points. And so we did 2 here, and we played with these things. That was review. Where's my other sheet? Oh, here it is. Find a solution that will simultaneously solve this one and that one. Wait a second. This was the first equation from previously. This was the second equation from previously. What does it mean to find a solution that simultaneously? It means solves both at the same time. Well, you should know based on the previous things, but let's graph them and let's see what we get. So y is equal to negative x plus 4. We already did that one, so it's going to be 1, 2, 3, 4, and it's going to go down one, right one. So here, 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 and here. And if I graph that, I get that one right there. I hope that's precise. And the other one was negative 1 for my y-intercept, and then up to right 3. 1, 2, 3, and then up to 1, 2, 3. And so it's going to be this. Right there. This is equation number 1. This is equation number 2. Okay. What's the one point that solves them both at the same time? Is it not this glorious little intersection right here? What point was that? 3, 1. If you go back and look at the previous ones, that was the point that was actually on both graphs. But not all points are on both graphs, only one. Okay, so now solving a system of linear equations simultaneously means you're finding the point or points where the x and y values solve all of the equations at the same time. So strategy for solving a system, which is what this is, of equations. Notice I didn't say linear, because sometimes they aren't linear, but this strategy is still the same. What's the strategy? You're going to, number one, graph them precisely. Because if you're sloppy with it and you're off where they intersect, then you're not going to get the wrong values. Okay? And number two, you're going to find the intersections. And those intersection points then are the solutions. So when two lines cross, there's only one possible intersection. So that's all we had right here. But what if you had a graph that looked like this? And this is just a little preview for stuff that might come later. Let's say you had your x and your y axis. This is x and this is y. And let's say that you had a parabola that did something like this. And then you have this other thing that comes through here, some kind of a line. How many places do those two things intersect? Well, they intersect once and then also twice. Okay, so how would you solve it graphically? You would graph them precisely and then find where they intersect. Those intersection points, those x's and y values, those would be the solution points that solve the system simultaneously. All right, so now let's talk about what the possibilities are, because sometimes two lines don't just intersect easily. You can probably find this picture in the book someplace or something like that. This is what we've been doing right here. When you have two lines that intersect in one location, there's exactly one solution for lines. Obviously, if it was a parabola like we showed earlier, you would have more than one, okay? The terminology, though, it's consistent. A consistent system is one that has at least one solution, and it's independent, okay? Now, the next one I want to talk about is this one right here. If you have two lines that are parallel to each other, do they intersect? No. So is there a single x and y value that will solve both at the same time? No. Okay, this is said to be an inconsistent solution. If you were solving this, you would say, well, there's no solution. There's no point that solves them both at the same time. Now, the one in the middle is interesting. How many lines do you see there? You're probably reasonable if you say one, but actually there's two. Or maybe even three, but in this case, we'll just call it two. There are two lines that are exactly the same thing. So it's a line, and then it's another line that's a different equation, but when it simplifies, it's the same line, okay? So there's two lines here, one right on top of each other. They don't just share one solution point like this one over here, and they don't share no solution points like this situation over here. All of the points of one line that solve it will solve all of the points on the other line. So this is said to be an infinite number of solutions. It doesn't mean that your solution is infinity. It just means that there's an infinite number of solutions. This is consistent because there is at least one solution, but it's said to be dependent. This point over here, what is that? That's 1, 2, 3. This is 3, 1. This is some point, but it doesn't solve either of those. So you can't say like all points solve it. That's not true. Only certain points do, but there's more than one. In fact, there's an infinite number of them. All right? So your strategy now, when you are doing solving systems by graphing, is to precisely graph them and then look for the places where they intersect. I hope your day is merry and bright, and may all your mathematics be right. But it's the mathematics that shows why it's right. I'm just saying. Have a good day.